All right, last time we left off, we had just started to talk about enzymes. Enzymes are probably the single most important macromolecule that we have in our body, or class of macromolecule, because their job is to speed up how fast a chemical reaction happens to the point where they're happening very, very quickly, as in kind of a split second worth of time. And where am I in that? There we go. So I ended yesterday talking about how enzymes end in ASE, and I talked about lactose with lactase. This example is sucrose. Sucrose is a disaccharide, 2 units, and it is broken apart by sucrase. Again, ends in ASE. If it's biology and it's a molecule that you see ending in ASE, it is going to be an enzyme. So keep that in mind. We're going to go through enzymes today and maybe a little bit more. We'll probably get mostly through this chapter and start working on the next one. Maybe. We'll see how it goes. Every chemical reaction involves breaking of bonds. In some way, breaking those bonds and reforming them in a different way. And it could be breaking them apart to make them smaller. It could be breaking them apart to make them bigger. But it involves breaking of those bonds. And you could almost think of them as chains if you want to. In order to do that, we have to overcome what is called the activation energy. And what that means is to get the reaction going, you have to put some energy into it. Like I've said repeatedly, if I have a slice of bread on the counter here, it will degrade over time, but there's really not very much in terms of energy going into there. There's some ambient air temperature that may contribute a little bit to the breakdown of the bonds between the molecules or between the elements in the bread, but maybe not very much, and that's why it takes so long. Activation energy can be overcome more quickly and lowered. In other words, we don't need as much activation energy if we are using enzymes. In catalysts, in catalysis, enzymes or other catalysts speed up the specific reaction by lowering how much energy activation you need. They don't affect the outcome. So it says here that they don't affect the change in delta G, which is just what's happening in terms of free energy. Wherever you were going to go, you're still going to get to that same spot. It's going to happen more quickly if you have an enzyme versus if you don't have an enzyme. You getting that, Owen? All right, so this slide is showing us a black line and it's showing us a red line. The black line is showing what happens if we don't have a enzyme present. So here I have my reactants. I wanted black. There we go. And I have my products. And we have our free energy here on the y-axis. And we have how long it takes to occur going here. Notice how there's a change in free energy from where you start here. Sorry, that wasn't very well drawn. To where you end here. It's always the same amount. So in this case, we have a given amount of energy that is it being given off or is it being absorbed by the products? Are we taking in energy, the products taking in energy, or are they giving them off? Look at the y-axis. They're giving it off. Yeah. So we're giving off some energy here. Energy is being released. So if energy is being released, it's supposed to be a G. Energy is being released. What kind of reaction is it? Exo or endothermic? Exo. It's exothermic because it is giving off energy. But we still end up in the same position. If it is black, this is without an enzyme. Or if it's red here with the enzyme. Okay. The amount of energy you need is less if you have the enzyme. Okay. Activation energy is less if you have the enzyme. Questions on that? That's a nice question for exams, to show you a picture and ask you something about that particular diagram. The reactant, the thing that the enzyme is going to be working on, is going to be called its substrate. And when an enzyme is bound to or attached to an enzyme, we call that the enzyme substrate complex. So it's just the two together is called enzyme substrate complex. And while it's bound, that's when the enzyme is going to lower that activation energy and cause that substrate or that reactant to be converted into our product that we want to have. A very key element in all of this is this phrase here, which is each enzyme is very specific. It's very picky. It will typically only work on one substrate. It'll only catalyze one reaction because it will only work with one substrate. And the reason why it's picky or specific is because it has an active site. And that active site is where it will interact or bind to or join with the substrate. And it only binds with it because it has a certain shape. So that active site has a certain shape, and that shape is complementary. It's complementary to the substrate. Back in the day, a long time ago, we used to think that enzymes and their substrate fit just perfectly, like a key in a lock. But it turns out that they actually don't, they sort of fit, but not, it's not a perfect fit. So once the substrate attaches to the active site, we have something called an induced fit that occurs, which basically means that the enzyme is going to clamp on to that substrate and it's going to make it fit in the active site. I'm going to show you a couple pictures of what I'm talking about here in a second. So here's my enzyme on the left. Looks like a big old Cookie Monster. And this tiny little thing here is my substrate. You notice anything different between between A, where I've got the enzyme, and B, where I have the enzyme and the substrate? Look at the shape of the enzyme. Has it changed? Yeah, it gives it a hug. Kind of gives it a bear hug. It wraps it around it. Cookie Monster won't give hug to. So okay, sorry. It's Tuesday. It's all I got. Wow. I teach this every year, so I gotta entertain myself. So anyway, it does. It gives it a hug. And in doing so, let's see if this is what I want on the next page. No, not quite yet. In doing so, I'll just say it and I'll come back to it. In doing so, it's going to strain the substrate's bonds. The bonds that are holding all of those elements together in that molecule will be strained by that bear hug that's given by the enzyme. And that will make it easier for the substrate to break apart. And that is responsible for lowering the activation energy you need. Talked about most of these things that are already here, or that are here. The substrate binds to the active site of an enzyme. Enzymes are very fast, like milliseconds fast. So fast that I've taught this for a long time, but I still can't understand how they can do it that fast. They're very quick. And you don't need a lot of enzymes because they're so super fast, and they don't get used up in reactions. So because they're not used up in a reaction, they can go back and do the job again and again and again and again and again as fast as you can, snap your fingers. They're back and doing it again. Cookie Monster, one cookie. Does Cookie Monster still eat cookies? Is that a thing? What? Well, there was a while where Cookie Monster became like the Veggie Monster. Where you were never in that. That was like, because you can't eat cookies. That's just wrong. So they made him a Veggie Monster. Yeah, right? It's terrible. They were saying it just wasn't, a good role model. I don't know. Do you all eat vegetables?
Nowadays, it would be seen as even worse to be like, cookies are bad. You should only eat healthily. I feel like it would be worse.
Even worse? C is for cookie. Do they still do that song? No?
Yeah,
It's good enough for me. Cookie, cookie, cookie. Starts with C. See, I don't want to teach today. So this is a picture of the big old purple blob here. Here's my Cookie Monster. And in here, that's my active site. I'll just put AS for active site. Actually, it's right there. And in that will go my substrate or substrates. Sometimes there's a couple substrates that are going to work together. And that is going to cause that those substrates to be weakened by the force generated by the enzyme, and it will convert it into my products. And then in the end, I've got different products, right? I went in with these two shapes and colors, and I came out with different shapes and colors representing different chemicals coming in. Gesundheit. But my enzyme stays the same. And my enzyme comes out of it, and nothing changes. Active site stays the same, and now it is, again, in a split second, ready to come back and do it again. The active site can lower the activation energy barrier by, one of the things it does is it gets, these molecules are it's not like there really is a Cookie Monster and it's out there seeking the right substrates. All of these molecules are just in motion. And they have to be oriented correctly in the active site in order to break apart. And when they get in, that enzyme helps them orient correctly and break them apart. Like I said before, they strain, the enzyme strains the bonds of the substrate, weakening them. And in some cases, they will actually physically, part of the enzyme will bond to the substrate. That substrate might have a particular charge on it. Maybe it's positive and the enzyme is negative, and that can draw the ionic bond apart to help weaken it and cause it to change its shape and break apart. The rate of an enzyme catalyzed reaction can be sped up by increasing the substrate concentration. So if you want to get more done more quickly, if you increase the substrate, you can happen more quickly to a point. If all of the enzymes are totally busy, I mean, if the enzymes are just back there hanging out and don't have enough substrate, then yeah, you can speed up the reaction. However, if all the enzyme molecules are functioning, if they're doing their job, then we say that that enzyme is saturated, meaning that that's as fast as it can go. It can't go any faster. The reaction cannot increase because all of those enzymes are engaged. All of the active sites are engaged. The only way you can overcome saturation is to add more enzyme. Because now if you add more enzyme, you can make the rate go up even higher. But if you see a graph and you see it maxing out like that, sorry, that's supposed to be max like that. The reason it has leveled off is because it's saturated, and the only way that we can make it go, this is reaction rate. The only way we can make it increase would be if we added some more enzyme to it, and then the reaction could go up some more. Again, it'll still level off eventually because all those enzyme active sites will be occupied. Questions on that? Now, I think this is the kind of cool part of the enzyme because it affects us in so many ways that we take for granted. We don't even realize that that it's enzymes that are actually affecting us and affecting how our body reacts. The enzyme's ability to do its job will be affected by things like temperature and pH. Also by chemicals that can influence the enzymes as well. There's some things that can speed up how fast an enzyme works, some things that can turn the enzyme off. But those are the general things that can affect them. Temperature is a great example of that. Each enzyme has an optimal temperature at which it can function. And I think I'll come back to that picture, that slide in a second. Yeah. So here I've got, it's got both of them actually. This top picture here. Oops, did that wrong. This top picture here is of two different enzymes. One, you can't see it from there. I'm sure you can't read it on your notes either. One is for a enzyme that works in a human body, and it's working around 37 degrees Celsius, which is our body temperature. And then there's another one here, a different enzyme. So this is one enzyme here, and then there's another enzyme here that works at a much higher temperature. I think that one says 75 degrees Celsius. Anyone ever been to Yosemite and seen Old Faithful? I have not, actually, which is kind of odd for me, but yeah. So living in those really, really hot water conditions are heat-loving bacteria. And inside of those heat-loving bacteria are enzymes that are adapted to 75 degrees Celsius. So very, very warm environment. If we took our enzymes and tried to heat up our body to 75 degrees Celsius, what would happen? Well, yeah, we would die. So going back to that slide before here, enzymes, it says it has an optimal temperature. If the temperature gets too extreme, that will cause the bonds of that enzyme. What macromolecule is an enzyme? Protein, yeah. So protein has a three-dimensional shape, right? And if that three-dimensional shape changes, it doesn't work anymore. Okay? So if you change that three-dimensional shape, you change the active site, and you also change the ability of that enzyme to work. So fevers work because they slightly elevate your body's temperature. And the bacteria or the virus that's infecting you has enzymes that like to work at 37 degrees Celsius. Well, if you bump it up to 38 degrees Celsius, they will be affected, and their proteins, their viral or bacterial proteins, will break down. That's something called, and I probably jumped the gun on it, but we'll just talk about it anyway. Denature. Yeah, when you denature a protein, you change its shape, and then it doesn't work anymore. Oh. So yeah, this is a great question. So, question is, wouldn't your enzymes break down as well? So, our body, if it's working properly, will only elevate the temperature a few degrees, so that we can still function with that elevated body temperature. It's not as pleasant, right? We don't feel very good when we have a fever. But we can still function, and our enzymes can still function. They might not function as well, right? Because I said that there was this curve. So maybe they're, working here rather than working right here where we would like them to work, but they're still working. Now, occasionally our body dysregulates and doesn't have an effective handle on the temperature, and then the temperature gets around, 103, 104. We saw a lot of that with COVID. We saw really high temperatures, really high fevers. That's the point at which you need to get yourself to the ER quickly, because at that point, then your own proteins will also become denatured. Okay, so you want to get that temperature, that body temperature back down. But I've actually heard from doctors that if your temperature is slightly elevated and you can deal with it, it's better to let it run its course and have that slightly elevated fever, because that's actually beneficial. Your body's doing that. It's raising the body temperature to fight off that bacteria by denaturing those proteins. Right? So, fun fact, I think. Another thing that can denature protein is the wrong pH. We talked about how when you form a protein, you form ionic bonds and covalent bonds and disulfide bridge bonds. There were van der Waals interactions, all these different things that went to making a three-dimensional protein structure. If you increase or decrease the ion content by changing the pH. Do you remember, let me ask you this, do you remember low pH has high or low amount of H positives?
Low.
A lot of H positives and very few OH negatives. Yeah. So if you decrease, for most of our enzymes, they work around a pH of 7. And so if I lower it down to a 5, if I go from 7 to 5, how many times have I increased my H positive concentration? If I go from 7, I heard it, to 5, 100. Yeah, I'm decreasing it 100 times. So I'm going to have 100 times more H positive. Okay? That's a lot of ions. That's a lot of charge. So if I have a negatively charged amino acid in that active site, it might be drawn or pulled out, and now the shape is wrong. And now that active site isn't going to work anymore. That's usually pretty catastrophic, either temperature or pH change. It usually means that if it's that bad, it's not coming back. Even in us, though, if you look at this bottom picture, bottom one's looking at pH now. There are two enzymes. One that works in the stomach called pepsin. And pepsin works at a pH of about 2. So it likes a very high hydrogen ion concentration. Trypsin, you don't have to remember the name of these enzymes. These are just examples for you. Trypsin works in the small intestine. Small intestine doesn't like high acid concentration or high H pluses. So it works actually at a slightly alkaline or basic pH. But in general, our body is right around 7. And anytime you have situations where your bloodstream becomes more acidic, that's going to affect all your enzymes. So, for example, if you're not getting in enough oxygen, or you're not getting out enough carbon dioxide, if you're not breathing out enough carbon dioxide, that can convert into carbonic acid. That lowers the pH, and that can cause all sorts of bad problems. Come on, go back. All right, let's just leave that there. Cofactors are non-protein helpers for enzymes. Good example of cofactors or coenzymes could be these things called vitamins. Cofactors can also be metals, so they could be like magnesium or zinc, right? Or you could talk about your vitamins, like your vitamin Bs, vitamin C, D, etc.
So why is the cofactor coenzyme? Why are they like different things?
Coenzyme is just a type of cofactor. Yeah. You really just need to know cofactors and coenzymes jointly. I'm not gonna ask you, and AP does not ask you to make a distinction between cofactors and coenzymes. Both of them help with the functioning of enzymes. So those are the good ones. Then we also have some things that can inhibit or slow down the progress of an enzyme. And they're kind of self-explanatory in their names. You have enzyme inhibitors that are called competitive ones. And those competitive inhibitors, their job is they've got, those inhibitors have a shape that is similar to the active site, or similar to, I should say, the substrate that the enzyme is working on. And so they will compete with the substrate for binding. And typically what happens is they get lodged into an active site and then they stay there. So the substrate can't access the active site like you would like it to do. It's actually shown in this first picture here. Here I have normal binding. Here's my active site here. But in the second picture, I've got a little blob that has a shape that's somewhat like the substrate, and it binds there, and then it just stays there. And then that substrate isn't able to bind with the enzyme. The enzyme can't break it apart. That's competitive because they're competing with each other. God, keep doing that. The other type is something called non-competitive inhibitor. And they also inhibit the enzyme from doing its job. And but they do it in a different way. And the way they do it is, rather than binding directly to the active site, they will change the shape of the active site itself so that it becomes less able to bind to the substrate. And that is shown in this slide, where now that non-competitive inhibitor binds, and it changes, if you look close at this shape versus this shape, it's different now. And so the substrate may still be able to bind or not. It's kind of hit or miss. But it doesn't do it as efficiently. And in some cases, it just doesn't do it at all, because it may change the shape so dramatically that it just can't bind at all. Non-competitive inhibitors are not good. And they can be permanent. So toxins, poisons, pesticides, even antibiotics for bacterial infections. The antibiotics can target enzymes. So if you start thinking about how to get rid of a bacterial infection, one of the things you could start doing is, well, let's see if we can change the bacteria's ability to copy itself, to make divide and reproduce. Well, to do that, you'd have to work on the enzymes, the proteins that are in that bacteria. So if you can change the shape of that enzyme, then the bacteria can't reproduce anymore. So that's how some antibiotics work. They inhibit those enzymes from doing their job. All right. I am going to stop there.